Hello everyone and welcome to part one of this week's lecture. In this lecture we are going to look at different applications of Bernoulli's equation, and in part two we will look at the application of Bernoulli's equation for two more specific cases, that is the steady state case, constant level tank, and then we will look at a more complicated system, that is non-steady state case, emptying tank, and see that how Bernoulli equation analysis change for these two systems. Then we will look at some of the flow measurement devices that are based on the principles of Bernoulli's equation, and more specifically we will look at pitted tube, orifice meter, and venturi meter. Okay, so let me quickly recap what you discussed in the previous lecture with Dr. Tom. You look at journal conservation law, and you specialize or tailored it into the form of conservation of mass. It means that the mass flow rate in a particular section will be constant. And in terms of energy, you again look at the derivation of this Bernoullis equation, and again it states that the sum of the three energies within a system at a particular section will be constant, while the individual constituents of energy can vary among these three terms, but the overall total will always be constant. Okay. And when you were driving this equation, you make some assumptions. You said that you have no viscosity effect. It means there are no losses. Then you said that you have an incompressible system. It means the density is constant. And finally, you said that your system is in steady state. It means that there is no accumulation within the system. It means that whatever is entering from this end will leave from this end. Okay. And if you now apply this equation between the 2 points to see that how the system or the fluid that is entering at point 1 is going to change into when it is exiting from point 2, you can apply Bernoulli equation, and that actually tells you how, for example, one form of energy can convert into another form of energy based on the shape and the geometry of the system. Okay. And again, as I said, if you apply it on different points, you can write it in this form as at point 1 and point 2. And according to conservation of mass, it should be the mass flow rate at point 1 should be equal to mass flow rate at point 2. And if you simplify it, you get this equation of continuity equation. And similarly, if you apply Bernoulli's equation at two different parts, you can see that you have this form of Bernoulli's equation. One thing that is missing in this equation is the loss factor, because we assume there is no viscosity effect, but in reality there are losses in the system. And I think in lecture 6 you will discuss that in much more detail, how to account for the losses in the system. It means that the velocity or the system that is entering on this point will incur some losses on along the length of the pipe in the form of pressure drop or in the form of heat. So you have to account for these losses in this equation. And here is a link of a very nice simulator for Bernoulli's equation, where you can actually, for example, change the geometry or the shape of the system, for example, and then you can run it and see that how by changing the velocity, the entrance velocity or the exit velocity, or the shape of the or the height, how actually different parameters are going to change. So please have a look at it and try to actually play with it and understand the concepts of different parameters on different forms of energy. Okay. So that is the general form of Bernoulli's equation. You looked at it mathematically and it makes sense, but what actually it means physically. So let's look at it. What is the interpretation of this equation? So if you look at it, you have, for example, here, that is H. You have the potential energy, that is mgh. And if you just consider H, it means that is H divided by mg. And mg is the weight of the fluid, so it means that H represents the potential energy per unit weight. Okay. Similarly, if you look in terms of kinetic energy, so you have half mu square, and if you divide it by m and again divided by mg, for example, so you have u square over 2g. So it will become again kinetic energy per unit weight. Okay. And similarly, you have the last term, that is P over rho g, and so that is a little bit less obvious to understand. So, but the way to do it is that if you multiply with the volume in the denominator and in the denominator, so you will have PV over mg. And if you know from thermodynamics that PV is work, and work is a form of energy, so we can write here, or we can understand it as a form of energy per unit weight as well. Okay, so all the terms in this equation are equivalent to energy per unit weight. Okay, and so similar to this form, we can have other forms of this Bernoullis equation. So we can write it in the form of energy per unit mass, and it means that you have to divide it all by mass. So, and if you divide the constant by mass, it will be another constant. Similarly, you can write it in the form of energy per unit volume. And in the next slides, next two slides, I have put the explanation of that. So please have a look at it at your time to understand that how we can write this equation in different forms of energy. Okay. So here, for example, you have the explanation of this equation in this form, and that is energy per unit volume, for example. Okay, so please have a look at it in your free time. Now there are some journal applications of Bernoullis equation. So people have put the Bernoullis principle to work by using reduced pressure in high velocity fluids to move things about. With a high pressure on the outside, the higher velocity fluid forces the fluid inside the stream, and this process is called entrapment. Okay, let me explain it here. So for example, here you have a system that you have a pipe that is with where the water is flowing, and then you have an opening here. Because the water is flowing at high speed, it actually reduce the pressure at this point. Okay, so here you have, for example, high pressure, and then when it travels, the pressure converts into velocity, and as such you create a slight reduction in pressure here, or a partial vacuum. It means that if you have air, for example, on this side, it will suck inside this high velocity fluid. Okay, and this is a principle that we use in many applications. So for example, we use this kind of device to create vacuum in containers. So for example, if you put a container on this side, and you open the water, you will see that because of this high velocity water flowing, the air will keep on going out, and then you will have a vacuum in the system. Similarly, for perfumes, this is the old style perfume dispenser, where you squeeze this bulb here, and as such you have high velocity air going out, and that creates a small reduction in pressure, and as such the perfume vapors, or the liquid vaporize and comes out with the air. Okay, so this example is what we call entrapment, and the similar concept applies to, for example, this London tube. You have a fast because the tube is traveling in this train is traveling in this tube that is enclosed, and that fast moving train is actually pushing the air in the tube, and that creates a kind of a suction at the back and on the side of the tube. Okay, and that is one of the reasons that there are always announcements that stand behind this yellow line. That is because you don't want to get hit by the train, but also because this fast moving train is creating a slight suction around it or at the back of the train. Okay, this is the same concept of Bernoulli's equation. And then you have another example of journal life example of Bernoulli's equation, where actually we can see that how we use the Bernoulli's equation to design the wing of a plane, then cause the plane to lift, for example. Okay, so here you have, for example, the wing of the plane, and you have the air traveling from this direction, from the left side to right hand side, and when the air hits the face of the wing, some of the air goes under the wing and some of the air goes over the wing. And the air that is traveling over the wing actually has to travel a longer distance, and it means that it has a higher velocity. And the air that is traveling at under the plane is actually at low velocity because it's a shorter distance. And because of this change in velocity, you have change in pressure as well. Okay, so high velocity air reduces the pressure on top side of the plane, and then you have low velocity fluid under the wing that actually increase the pressure. And because of this increase in pressure, you have the lift. Okay. And if you, for example, next time if you are traveling and you get the chance to sit to the window seat, have a look outside the plane. That when, for example, the plane is in taxiing mode, you have this plates on the wing that are actually straight. But when the plane is actually landing, you have these plates up. And the reason for that is that because now when you are landing, you want to reduce the velocity of this high velocity air, and as such actually you don't want this effect of lift. Okay, so you are reducing the velocity of the air on top of the wing, and as such it means that you will not have a pressure difference between the top of the plane and the bottom of the plane. Okay, that is all for part 1, and in part 2 we will look at again the Bernoullis equation in terms of more chemical engineering related applications, that is steady state case and non-steady state case. Okay, see you in part 2.